this class, the microphone doesn't like me. I don't know why. Okay, let's get started. Okay, so I checked all the homework's graded up through now. I've got the attendance grades up to date, so we're rocking and rolling. How did the section homework go? Hopefully it wasn't that bad. I have a homework that I am giving you today. It is not due Monday. It is due Wednesday, okay? It is due Wednesday because in order to fully explain the goal of that homework, which is to compute the deflection in trusses, I need today's lecture and Monday's lecture. Today is going to be a little bit like movie time because we're going to be explaining some things about energy-based methods and virtual work. And then my lecture on Monday is where we go through a full-blown example. One thing I'll say is that homework 4 is the last homework before the celebration, okay? And it is the last topic of coverage on the celebration. Homeworks 1 through 4 is the coverage of the first exam. Speaking of lecture Monday and Wednesday, we're not going to be here. I'm going to be out of town. So what I'm going to do is post, I've already recorded these lectures. I'm going to post them to the playlist after today. And I'll post this lecture, the one I'm recording now, and make it live. And then Mondays and Wednesdays, I'll make them live as the days come. Now on Monday, what we're doing Monday is we're discussing deflections and trusses. What I'm doing on the Wednesday lecture is I'm discussing your project in the class. There are 2 submittals for the project. The first submittal is not due until the middle of October. Okay, so it's a little while from now. And what I'll say about the project, I say this in the video, it is not intended to be a lot of work. I mean, it's a little bit different, you know, than what we're doing here, but it's not intended to be a gargantuan amount of work. And the first submittal is really light in terms of the work requirements. All you got to do is lay out 3 trusses and select one. It's really not a lot of work. Okay, any questions? Okay, today what we're going to do is we're going to shift gears a little bit, and we're going to talk about an entirely different aspect of structural analysis, and that is deflections. Okay, deflections, deformations, essentially the same thing. Okay, up until now, what we've been focused on is looking at forces in structural analysis. So we have a system. What are the reactions required to keep that system in equilibrium? Those are forces. Okay. What about trusses? We analyze the truss to determine the internal forces in each member. That's what I mean when I say forces. Now, I'm not saying those aren't important. They're incredibly important. You need those values in order to design. But that's not the whole story. Okay. Every structural system that we utilize, when we apply forces, the system responds by deforming. Okay, it undergoes some degree of deformation, some degree of deflection, some degree of rotation, etc. That's what we're going to be taking a look at now. And we're going to start with trusses. And the reason that we start with trusses is because the mechanics, the underlying mechanics for solving for deflections and trusses are among the easiest to deal with. Okay. Deformations are incredibly critical to understand in structural engineering for a couple of different reasons. One of those is that we usually have deflection limits that structures have to satisfy. So as an example, we're in a building right now and we have beams and columns all over the place. So if we're looking at, let's look at the ceiling here. So above this drop ceiling, there's a series of beams and girders that are supporting the weight of the floor above us. Okay, so let's say there's a floor beam that's going from this column right here, and it's connecting this way. Well, when we design that floor beam, we're going to have to understand the forces that are applied to it, so things like the shears, the moments, etc. But on top of that, when that floor beam is subjected to load, it will deform, and so there will be limits on how much it can deform. A common limit that we use in building design is L over 360. So we take the length and we divide it by 360, and whatever that distance is in inches is the maximum amount it can deflect. That's a common one for buildings, and we'll talk about a little bit later about why that is. So we'll have multiple limits that our systems need to satisfy. The other reason for understanding deflections is because it is the relationship between applied forces and resulting deformations that makes indeterminate analysis possible. You cannot analyze a statically indeterminate structure without understanding this relationship. If you remember, statically indeterminate structures are when we have more unknowns than we do equations of equilibrium. So how do we solve for those additional unknowns? We utilize the relationship between applied loads and resulting deformations. And it's that relationship that drives all sorts of advanced analyses. So if you've ever heard of, and we'll talk about it later, but if you've ever heard of finite element analysis, that's how finite element analysis works, is it categorizes that relationship. And don't worry, if you've never heard of that, we will discuss that a little later. Now I want to show you off the bat, right at the very beginning, how we solve for deflections. Because usually, I know how engineering students sometimes are, is they're like, just tell me the answer. Just tell me how we do it. So I'm going to, but I need you to understand why, because the method is a little different than probably what you're expecting. So I'm going to consider the following truss, okay? First off, is this truss familiar? We did this truss, we analyzed this truss in class. This was our first in-class truss example. We analyzed this truss, okay? Now, I have here an illustrative example. Let's say our goal is to determine the vertical deflection at B. So what I mean by that is, here's the structure. I've got 10 kips here, 15 kips there, 20 kips there. When I apply load, I propose that the structure deforms. And I want to know, after we apply that load, how much it deforms at B. Specifically, how much it deforms vertically. Okay, so that's going to be the goal. We're going to use that just as an illustrative example to show you how this works. Okay. Now, one thing worth mentioning is that there's some new stuff here in our model. For each member, I've given you another piece of data that I didn't give you before. I'm giving you the area, right? So, in other words, if I take this member, let's say this member BC, I take member BC and I samurai sword or lightsaber through BC and I look at BC, I got an area of 4 square inches. That's how big member BC is. With me so far? So I propose that in order to do deflection computations, we now need to start to look at the constitutive properties of the structure. We either need to know them in advance or they need to be a goal of the problem, like to solve for them. Okay? Well, we not only need areas, but we also need material properties. And so for the sake of discussion, I'm going to assume that this truss is made out of aluminum. And the Young's modulus, or the elastic modulus of aluminum, is 10,000 KSI. Those of you that have had mechanics and materials, you know what I'm talking about when I mention Young's modulus, right? The relationship between stresses and strains. Okay. Now, ultimately what I'm going to be arriving at is the method of virtual work. Okay, that's going to be the method that we use to compute deflections in the course. And as I said earlier, I know sometimes engineering students, all right, look, Dr. Mike, just tell me how it works. Okay, so this is how it works in a nutshell. Okay. So the first step is you perform what we're going to call real analysis. And real analysis is just taking the truss and analyzing it for the loads that were originally on the structure. So we compute the reactions, analyze the truss, and we get this. We've already actually done this truss in this class. And so these numbers that I'm coming up with right here, this is what we did before. Okay? Are you with me so far? So here's the original structure, the real structure. That's step 1. Step 2 is to take all of those loads off the structure and do the truss analysis again. But the second truss analysis, which I'm calling the virtual analysis, is a very particular truss. We take the original truss and we put a single load on it. Where do we put that load? We put it at B. Why do we put it at B? Because we're trying to find the deflection at B, right? So that's where we put the load. I'm putting the load downward because I'm interested in vertical deflections, and I'm going to place the load downward because I'm assuming that this joint deflects downwards after all these loads are applied. And the magnitude of that load is 1. We'll get to that. We'll get to why that is here in a bit. But for now, if you're the engineering student that just wants to know, just tell me how to do it, that's your answer. Okay, so we place a single unit load. The method of virtual work is sometimes called the unit load method for this reason. So we analyze the truss and we get a whole new set of forces. Okay, so I have some particular notation. I'm using capital F's or big F's for the real forces and lowercase f's or little f's for the virtual forces. And so for every member, there's a real force and a virtual force. Real force, virtual force. So far, so good? That's step 2. So step 1 is the real analysis, step 2 is the virtual analysis, and then the third step is we sum up energy components for each member. And the way that we do that is we sum up the following quantity, little f times big F times L divided by EA. We sum that up for every member, and whatever the answer is, that's our deflection, okay? Now some of you are like, where did he come up with that? Don't worry, we're going to explain it, okay? We'll get there. But if you want to know just how to do it, that's how to do it. Now, when it's all said and done, I know this is really tiny here on the slide, but don't worry, we're going to blow it up later. The sum here is 0.237. It comes out as a positive number, so it's 0.237 inches, and since it's positive, it means when we assumed a downward deflection, we were assuming correctly, and the answer is 0.237 inches deflecting downwards. And that's how you compute deflections in a nutshell. So if you wanted, you could sort of just, use that knowledge and actually do homework for yourself right now. There's really theoretically nothing stopping you. But I want you to kind of understand what we're doing and why we're doing it. Because I'm sure some of you have some questions like, where did you come up with that? Don't worry, we're going to get there. All right. Now, where this comes from is from a method or a class of analysis tools in physics called energy methods. Okay, and so what I want to do is I want to talk about energy methods and talk about the different types of energies that structures see. And some of you are thinking, wait, energy methods, that sounds kind of fancy. It's really not. Everybody in here has done energy method problems at some point or another. Everybody has. Let's go back to the law of conservation of energy. Energy can't be created or destroyed, right? It just gets converted from one form or from one form to another, right? So, for example, we've got here a screenshot from a very awesome video game. We've got here this Goomba. This Goomba here is sitting on top of this platform, right? The Goomba on top of the platform has a gravitational potential energy of mgh, right? Then as the Goomba walks off the platform, the Goomba starts to fall, right? Goomba starts to fall, that potential energy gets converted into kinetic energy, which we can convert, or we can compute as 1/2 of mv squared, right? Then when we can recognize that since energy cannot be created or destroyed, we recognize these two energies are equal to one another. Since if we set these two quantities equal to one another, we see that the m term cancels, right? So this is how we know in physics that neglecting air resistance, if we drop a bowling ball and a marble off a building, they fall at the same rate, right? Everybody's done this before, right? I propose that we are going to apply the same concept in structures. And how's that going to work? Well, we're going to go to a different video game, okay? So let's say that we've got, Link here, and Link here's got his bow, and he's drawing the bow to shoot the arrow. Okay, how's this working? Okay, so I have here a rubber band, and I have here some ammo, right, from I'm sure you've never done this in middle school or high school, am I right? Never happened, right? Okay, so how does this system work? Okay, so I want you to think of the rubber band as my structure, okay? So I'm taking the structure and I'm applying a deformation to it. I'm deforming the structure. What's happening as I deform the structure is I am storing energy inside the rubber band. And that is evident by letting the rubber band go and it doesn't fly out, right? But the other thing worth mentioning is what happens if I take the rubber band and I pull it back really far. In order to pull it back really far, I've got to use more force, right? I have to apply more load. But with that more load comes more energy because now it goes even further, right? So there's a relationship between the amount of force that I apply to the system and the amount of energy it stores, and also the amount that I've deformed it. The further I've deformed it, the more load that's applied, the more energy that's stored. Does that make sense? So there's a relationship between deformations and energy. And that's kind of what we're getting at when we talk about energy methods, is we're saying we're going to use that relationship in order to sum the, in order to compute deflections. Okay, does that make sense? All right, so I want to go through some basic terms and some basic notation because I'm going to be using this throughout the slideshow. What we're going to do is we're going to look at two different types of energies that a system's being going to be subjected to. We're going to use the terms W and the term U. Okay, W is going to correspond to the external work done to the system. So if we think about my rubber band analogy or the link drawing the bow analogy, W corresponds to the relationship between applying the force and the arrow moving, that force times distance. U is the stored energy, the amount of energy stored in the rubber band or stored in the bow. And I propose that those two have to be equal to one another in order to conserve energy. Okay? So for all scenarios, this external work done has to equal the stored energy. Okay? A couple notes before we move on. So we're going to assume for this discussion that all of the behavior of our structures are linear and elastic. Okay? In other words, they behave like the rubber band. If you go back to Engineering 216, what does linear elastic behavior mean? You have a system, you apply load, it responds in a linear fashion, and elastic means that if you let that load go, it reverts back to its original shape, right? And that's what we're going to assume for structural behavior, and that is the case for most structural analysis problems in the real world. It's not always the case. There are some instances where you consider nonlinear analysis, like in seismic and dynamics and things like that. But for the most part, most everyday structural analysis is considered linear elastic. Now, we can consider other forms of structural response, like torsional response, thermal response. For the types of analysis problems that we're looking at in here, we can kind of neglect these. My main point with this note is that you can use energy methods to solve all sorts of really simple problems or complicated problems. That's why it's so ubiquitous in advanced analysis and whatnot. Okay, so I want to look at external work done. Okay, so let's take a bar, let's take that bar and let's stretch it some amount delta. Okay, so I propose that what I can do is I can say from an external work perspective, the more load that I apply, the more deformation that I get. Okay, all right. And if I'm trying to quantify the total amount of external work done to the system, I propose that that's going to be the area under this curve, right? Breaking it back to Matthew 29, right? But because we're dealing in linear elastic behavior, no need to break out the stretched out curly S's, no need to break out any integrals because it's a triangle, right? So I propose that the total external work done, if the load was applied gradually, and that's kind of the case, right? Because here's the system and I'm applying the load gradually. So as I apply the load gradually, the external work that's done is P times delta over 2, just base times height over 2. And that's the external work done to the system. With me so far? And let's keep in mind that my goal right now, if we're thinking analytically, what's my goal? My goal is to try and determine this value delta. That's what I want to know. I want to know what delta is. I want to know how much it deforms. Okay? That's my goal, delta. Now that's the external work done. What about the stored energy? Okay? All right. Let's go back to mechanics. Does anybody remember, if you have an axially loaded bar, how you determine the deformation? Does anybody remember that formula? You take the applied force times the length divided by that. Y'all remember that? Now, where does that come from if it's been a while since you've looked at that? Where does that come from? Well, we've got our sigma equals F over A, right? Axial stress formula. That should be pretty familiar, right? We've got our constitutive relationship, Hooke's law, that the relationship between stresses and strains can be defined by a constant of proportionality, which we call the elastic modulus or Young's modulus. And then we can say that strain is the change in length divided by the original length. Is this bringing it back? Ringing a bell? Change in length over the original length? So what I'll do is I'll take this first equation and instead it's a sigma. So what I'm doing here is I'm saying sigma equals E times the strain, and instead of sigma, what I'll do is I'll say, let's not write sigma, let's write F over A, and then instead of this, let's write change in length over the original length. So that's where this comes from, and then I'm just solving, right? So I get delta equals FL over EA. And so what I can do is I can write a similar curve, and I'm saying that for every amount of internal force, for every unit of internal force that's inside the system, I can increase a corresponding FL over EA. That's the deformation. Does that make sense? Okay. So the stored energy is the area of this triangle, which is 1/2 base times height. And so that's where I get this expression right here. Okay, does that make sense? All right. I don't want to go too fast in this. And again, if there's a detail here and there that you miss, don't worry, it's not the end of the world, but I want to make sure conceptually you're kind of following along with what's going on. So far, so good? Okay. So, now one thing I do want to mention, some of you might be getting a little worked up about the notation. Like, why am I using P's for the work, but F's here? Okay. Well, what I'm saying is there is a difference between the applied force externally and the resulting force internally. And the best way of describing that is to go back a few slides and like look at this, okay? So for example, the analogy would be that my external forces, like the 10 kips, the 20 kips, and the 15 kips, those are my P's, right? The F's are what the members see. And we know from truss analysis that just because you put 20 kips here doesn't mean that all these members see 20 kips. They're different. There's a difference between the external load and the internal force. Does that make sense? That's why I'm using different notation. So if you're seeing that and you're going, wait a minute, what's going on here? That's what's going on. Where was I? There we go. All right. So far, so good? Okay. So let's summarize where we're at so far. So if we use the conservation of energy, you know that W has to equal U, what do we got? So for a single member subjected to axial load, we have the external work done, and we have the stored strain energy. Okay, that's for a single member. What about a system of members, like, oh no, a truss? Well, if we have a system of members, the external work done is 1/2 P delta. The stored energy is just summing all of these for every member in the truss. Okay? Everybody kind of getting the idea? Okay. Now, energy methods, what they do is they allow us to solve for deflections at a given point, but in order to quantify that energy, there's kind of a problem here. In order to quantify the external work done, we need a load at the point in question. See, what we're doing right here, what this method is that you see right here on the screen, well, you see this right here. This method is called the method of real work, okay? So what we're doing is we're taking the stored energy and the external work done. We can set those two equal to one another and solve for delta. But there's a problem is that so that's the method of real work. There's a big problem with that, and it's about the applied loads, okay? So let's talk about real loads and let's talk about virtual loads. And specifically, like we've got an energy method that I think conceptually kind of makes sense, but it's not enough, okay? Here's the problem, okay? The issue with this formulation, this method of real work, is the formulation of the external work done. I have that the external work done is 1/2 of P times delta, P being the external load applied. Remember that last truss that we saw? How many different loads were on that truss? There were like 3, 4 different loads on that truss. So which one do you use? Well, it's not that simple, right? You can only solve for deflection where the load is applied. If you've got multiple forces on the system, if you've got multiple loads on the system, that makes that pretty difficult to isolate the deflection in question. And it is very common in real world structures that you have a structure with multiple loads all over the place. So the method of real work is not enough, okay? So how do we handle this? Well, we handle it by putting a load where we want to find deflection. We place a load at the point of interest, okay? So what we're going to have is we're going to have a structure with two sets of loads. We have a structure with a single load applied at the point of interest and a structure with the original load, okay? And so we're going to get kind of clever with how we handle our energy, and we're going to get kind of clever with how we do the math, and we're going to do some tricks to make our lives a little easier from a mathematical perspective. So let's go back to our bar example. So what happens when we apply two loads? Let's go back to our bar example. Let's see if we can clarify things. Let's see if we can flush things out a bit. So the first thing that we're going to do is we're going to apply P1 gradually. P1 is our virtual load. And the way I like to describe P1 is it's a fake load. It doesn't exist. It's not really on the structure, but it's sort of like a marker. You know, it's sort of like, you know how in medicine they'll inject you with the stuff, so like when they put you under the MRI that they can see what's going on. That P1 is kind of like that. It's kind of like a marker that will allow us to track the energy at the point in question, okay? So P1 is, again, it's a fictitious load, okay? But first we're going to apply P1 gradually, and the bar is going to respond by stretching some amount, delta 1, okay? Then what we're going to do is we're going to apply the real loads. P2, that's the real load. P2 is what's really on the structure. And so at the end of the day, the total load is P1 plus P2, and the total deflection is delta 1 plus delta 2. Does that idea kind of make sense? So let's look at what happens when we graph this out. Now remember, our ultimate goal is to solve for this. I really don't care what delta 1 is, because delta 1 is the deflection due to this fake load which I made up. I care about that, because that's the real deflection corresponding to the real load. With me so far? So let's graph some things out. So I got a load displacement curve here. So let's see what this looks like. So the first thing that I do is I put that fake load on there, right? So the fake load, I've got P1, it corresponds by deflecting some amount delta 1. Then I put that additional load on top of it. So what I've got now, when it's all said and done, is P1 plus P2 corresponding to a total deflection delta 1 plus delta 2. The more load that you apply, the more deflection that you get. Does that make sense? So what I've got is this triangular region, and I've got it split up into these different areas. I don't get worked up with the numbers. I called it W1, W2, W3. I'm just so that we have something to reference. Let's see if I can write these out. So, you know, this is just, you got to pay attention to your algebra. So we got 1/2 P1 delta 1, that's this one. This one, so it's P1 delta 2, and then this one is 1/2 delta 2 P2. All right, you see what I'm doing here? All right, let me take a step back and see. Does anybody have any questions so far? Okay, so that's my external work done. What about the stored energy? Okay, stored energy is kind of the same thing. Okay, now I'm going to use some notation here, and this should be a little familiar. Okay, the little f's are the internal forces generated by that fake load, and the big F's are the internal forces generated by the real load. Okay, so what do we got? We've got, you know, it's the same story. We got little load, little deflection, big load, big deflection. But let's look at the notation, right? Little f corresponds to little FL over EA, and what do we get here? Little f plus big F corresponds to little f plus big FL over EA. And then what do? We write the energy terms the same way, right? So we take this area, 1/2 base times height, this one, base times height, this one, 1/2 base times height. A lot of symbols, I know, but does the idea kind of make sense? All right, so let's take a step back. All right, so let's separate it out. So there's my external work done, there's my stored energy, right? Right? Now, what did we say? We said that energy can't be created or destroyed, right? So this energy component has to equal that energy component. Now remember how I said we were going to get clever? Here's how we're going to get clever. I propose that if W equals U, if all these correspond, then W1 has to equal U1, W2 has to equal U2, W3 has to equal U3. And so instead of dealing with all this hullabaloo, I'm only going to deal with the rectangles, W2 and U2. So I propose those two equal one another. In other words, this term equals that term. So I want to take this box, and I really want to kind of focus on it a little bit. Let's see what's going on in here. So on the right, we've got some stored energy terms, right? But what's going on the left? What's going on the left? We've got P1 times delta 2. What is delta 2? That was our goal. We wanted to find the real deflections, right? P1, that's our fake load, right? That's our fake fictitious load. Now my question for you, my final question, if you were trying to make this as easy as possible, what would you choose for P1? 1, right? we would use the value 1, because if P1 is 1, we would get delta 2 is that. That's the method of virtual work in a nutshell. Remember how we said that we would apply a unit load, and the unit load is 1? That's why. Remember, P1 is our marker load. We can choose what, we wanted it to be this fictitious load that we could use to track the energy. So we can choose whatever magnitude we want for P1. And so what's the mathematically the easiest term to choose? 1. Make sense? That is the method of virtual work. Okay, that, and I think now the crazy theory stops so we can digest what's going on here. So let's get into this a little bit. Okay, so this is the method of virtual work. It's also known as the unit load method. And what is it? It's an energy-based approach for computing deflections. Okay, the reason why I like the method of virtual work so much is because it will work for any structure subjected to any type of loading, period. Okay, and let me talk about that for a little bit. So if you open your textbook has 2 different chapters on deflections, and it has one chapter on energy-based methods and one chapter on geometry-based methods. And what you'll find is that, there's oodles of different ways of computing deflections, especially when you get into geometry, but you find that those methods have certain limitations or certain advantages. So I'll give you an example. There is a method for computing deflections in beams called the conjugate beam method. And it works fantastic when you have a bunch of point loads, because it does make the math a little easier. But whenever you have distributed loads or things like that, it can actually get a little, the math and whatnot can start adding up. But the beauty of the method of virtual work is it'll work for any structure, anywhere. And so it's one of the reasons that I focus so much on it on this class, because 1, it's really easy to remember how to do it, and 2, it works all the time. So it's really fantastic. Okay, and so we're going to use this method later for beams and frames. Right now we're just looking at trusses, but later on when we get to beams and frames, we're going to go back to this method. Okay, so let's go back to that example. Let's go through that example again. So here's the truss. Now remember, the truss, we got more data than we did before. Now we've got areas and we've got Young's modulus. Why? Because we need those quantities in order to start computing deflection. So we've got to have E's and A's in the picture. Okay? Later on when we look at beams, we're going to have E's and I's, the moments of inertia. So what do? We solve the structure. We start off by determining the real forces inside the structure, and so we get a real force for every member in the truss, and then we apply the virtual load. Okay, so we take all the loads off the structure, we remove them all, and now we have a new structure with just a single load on it. That magnitude of that load is 1, because remember, if we set P1 equal to 1, that'd be the easiest case from a math perspective. We apply it vertically, because for this problem, we're interested in vertical deflection at B. So for example, if I asked you a different question, I said, here's the truss here, here's this truss, what's the horizontal deflection at E? What I would do is I would place a single horizontal load at E. There'd be nothing else on the virtual structure but just a horizontal load at E. What direction do I place it? Whatever direction I assume the initial structure is going to deflect. If it was me, I would look at this structure, I would say E is probably deflecting to the right, so I would put a single horizontal load to the right at point E. The magnitude is 1, and you assume the direction. And what do? You analyze the structure. Now, technically, the unit load is a load of 1. If you want to think of it as 1 kip, you can, like you put a 1 kip load. Technically, it has it's unitless, so the resulting internal forces are unitless. So, yeah, there is one downside that you do have to analyze the structure twice, which is why your homework's due on Wednesday instead of Monday. But the upside, hopefully, is that you can do things like recognize symmetry. You can recognize maybe there are 0 force members. So there might be a situation where a truss did not have 0 force members for the real structure, but for the virtual structure it might. You know, this structure is symmetric. So all we have to do is analyze that joint, maybe that joint, and then we're done because it's all symmetric, right? So it's something to think about. If you can exploit that, exploit 0 force members, it can make your life a little easier. And then now we apply the method of virtual work. And what is the method of virtual work? We say, okay, we've now got 2 sets of analysis results. We've got our big F's and our little f's. The big F's are in kips, the little f's are unitless, okay? So here's our expression. We take the little f's, the big F's, the L's, the E's, and the A's, and we sum up our energy components. So let's talk about units. So the E value is in KSI, the area is in square inches. Now I haven't mentioned anything about the member lengths. What units should I put the member lengths in? So what do we got? We got kips, KSI, inches squared. What unit should the member lengths be in?
Inches.
Inches. So whenever you perform your calculations, convert the member lengths to inches, okay? So the way I like to do this is I'm an engineer, I love tables, so I like to set this up in a table. So what do I have? I have a little f, big F, L, E, A column, and notice how the member lengths are in inches, okay? And so we record all this. I go in and I place my little f and big F values. It's customary in your table to report the tensile forces as positive and the compressive forces as negative. You could do that inverted, it wouldn't matter, just as long as you're consistent, okay? So for every member, so I go back to the truss analysis and I say, oh, member AB, for the virtual structure it was this in tension, and for the real structure it was that in tension. Tension, tension, okay, this one was in compression, so it's negative, and this one's in compression, negative. And then for every row, I say, okay, little f, big F, L over EA. Little f, big F, L over EA. Little f, big F, L over EA. Anybody think about a program that we might use to make our life a little easier? This is an Excel problem in there, right? This will make your life a lot easier on a homework assignment to utilize Excel to do the calculations for you, okay? So what do? Little f, big F, L over EA, do that across the board, calculate each of these, and when you sum it, you're going to get an answer, okay? Now, if you track the units for each of these energy components, the units for these energy components is inches, right? So sum all this up, and I propose that, so, I mean, here's what we've got. We've got P1 delta 2 is the sum of little f, big F, L over EA, and what we're getting is 0.237 inches is P1 times delta 2, and how much was P1? 1. So delta is 0.237 inches. So again, whatever that sum is, that's your deflection. It's that simple. And so we got the deflection was positive, which means our assumed direction was correct. We put that virtual load going downward. The deflection at B in the y direction is 0.237 inches going downward. And that's it. That is the method of virtual work. So like I said, I knew today would be a little different. It'd be a little more like movie time, but I want to take a step back and see if this made sense. Does anybody have any questions about the idea, about the concept? So I want to show you something. Let me go back, or let me pull something up real quick. So like I said, Monday and Wednesday are going to be pre-recorded lectures. On Monday, because I know I dumped a lot of like math on you. I dumped a lot of theory, a lot of physics on you. It's Friday. You're like, come on. It's the weekend. We're tired. Come on. Okay, so I know it's going to take a while for that to seep in. That's okay. Like I know it's way different than a lot of the other lectures that we have. So I want that knowledge to seep in a little bit. Okay, and so lecture 12, this is the first pre-recorded video that I have this week. I go through and summarize this stuff again, but then we spend most of the video doing this. So this is another example. I'm giving you a truss, and we're going to determine the vertical deflection at C and the horizontal deflection at joint B using the method of virtual work. So I'm having you go through the process together. Okay, so we'll do a full-blown example, start to finish, in the video on Monday. Wednesday, we go through the project a little bit. One thing I'll tell you, so I'm assigning a homework today that's due Wednesday. I would give you a piece of advice to go ahead and solve the truss over the weekend so that between Monday and Wednesday you don't have a bunch of work that adds up. It's just a piece of advice to go ahead and solve the truss. Any questions? All right. Trying to to think if there's anything else that is worth mentioning off the top. Can't really think of anything. One thing that will happen on Monday is there'll be some notes that populate for the analysis project. I'll go through it on Wednesday on the pre-recorded video there. Again, the submittals aren't due for a while, but just as long as you watch that and have that handy for the first submission, you'll be good. I have gone ahead and posted attendance grades for Monday and Wednesday. I assumed everybody was present, so everybody, because it's not your fault that we're pre-recording the lecture, so I figured that made sense. Any questions? Not only are you getting Monday and Wednesday off, but you're getting 9 more minutes. I'm going to pull up the code. That's all I got. I will see you all next Friday.